inconvenient. Do you see my presentation?
Yes, perfectly.
Yeah. Okay, sorry. Yeah, welcome to my talk about unsupervised approach for online outlier detection in industrial process data. It's a work that was done by that I've done together with Michael Bechny. After a short introduction, I will describe the problem definition and summarize its main challenges. Then I will give an overview of our technical approach that we came up with in order to face these challenges, presenting the evaluation results and conclusions will close my talk. The presented work was done within a collaboration with one of our industry partners that produces plastic parts using injection molding. Maybe in very few words, how does an injection molding machine work? Material is added here to the machine and then brought forward by a screw and is heated and is then injected. The liquid plastic is injected through a nozzle into the mold that we can see here, a sketch. Typical a mold consists of multiple cavities. That means with each injection shot, multiple parts of product are produced. At our customer, they are typical also more than 100 parts of product that are produced with one shot. Shortly to that you can have a picture with that we have to handle quite a huge amount of data. Our industry partner has a machine park with several hundreds of machines. He produces various, that is, several dozens of different products, and each machine produces up to hundreds of thousands of product parts per day, and with each shot, hundreds of measurements are collected. From experts at company side, we know that there appears the problem in the process that of not proper filling of one or more cavities within a single shot, and the goal of this task here was to build up a monitoring system that detects such cases on different machines and different products simultaneously. The first step in this work was feature engineering and selection, so this was most of all driven by the experts at company side, and we ended up with five feature streams, of which the experts were confident that observations of multidimensional outliers of this within these five data streams point directly to exactly this problem state. So the concrete problem that we had to solve was multivariate outlier detection on 5 selected features. Here on the right side, you see 4 such examples of data streams, and one sees that these data streams can differ quite a lot, coming from different machines for different products, and different process states. I will now state the main challenges we had to face in this setting that actually hindered us from simply applying standard outlier detection methods. First of all, we had to face a highly varying amount of outliers in the data. There were many production periods. There are many production periods where no outlier is detected, like here in the green marked sequence. That is, so to say, the normal state. There were cases where, like here in the red marked sequence, where just a few outliers are appearing over a longer period. But there were also very frequently cases when the problem appeared very often, yeah, where we have outliers from up to 30%, what actually is a contradiction of the definition of outlier as a rare event, making also in this case standard outlier detection hardly feasible that then should work for all these cases. Another challenge was that we very often could observe that the outliers appear on a very similar value level, like we see in these three examples, and this was simply caused that by the fact that there was the same cause that, for example, if one cavity is not filled properly, it had the same consequences than in the data. But this means that the outliers themselves form also a quite frequent cluster, and this makes, again, density-based detection methods difficult to apply. Yeah, last but not least, a challenge was the fact that our data streams contain contemporary non-stationary structures, like, for example, here in the red marked example. We have also to deal with, we have to have in mind that we have to deal with an time-related evolving manufacturing process. For example, here we had always, after production breaks, we had some starting phase where we had certain trends, yeah, and we had to deal also with this. Also in these phases, we wanted to detect the problem, yeah. And another thing was still that due to different machines, different products, often the same features were on a totally different scale, like here. Yeah. I want to present now our sketch of our approach with which we came up and tried to manage to tackle all these challenges at once. The core idea behind is to generate a multivariate prediction model that robustly captures the contemporary structure of the data and use the predicted future states together with the estimated prediction intervals to detect then the outliers among newly arriving observations. So the whole approach was also a condition should be online algorithm. The approach consists of three consecutive main steps. At first, there is a starting phase that helps to detect early outliers before enough data, till enough data is collected to make a reasonable model initialization. And additionally, it enables us also to avoid a bias at the next step of the model initialization. So to start with somehow clean data. In the second step, after transformation to comparable scales, of the input data, we use this data of the starting phase to initialize a vector autoregressive model. In the third step, we then make incremental model refitting. I will try now to, I'm already quite far with the time, but I will try now to shortly say more details about these three steps. We here in the starting phase, we try to approximate the possible trend in the data by model averaging using online Bayesian regression. For this, we took the evolving data stream, that data points arrived one after the other, and trained different simple basis model, and then calculate a weighted prediction that are that is the violet dashed line, and the weighted where the weights are based on the Bayesian information criterion, and then estimating prediction intervals, we can estimate data points like this red dot that are outliers because outside of the boundaries. In the second step, follows then the initialization of the model, of the vector autoregressive model, based on the first observations of the staging phase. And maybe important is to mention what here was decisive was that before the model training is conducted, the input data is standardized. But instead of using the usual sample statistics like sample mean or sample standard deviation, we used estimations from the Bayesian regression in the step before. And finally, the main phase 3, that is an iterative procedure where the main procedure is that in each step, when a new data point is arriving, I use the recent predictions and residuals of the current model to, in a first step, dynamically transform the newly arriving data point, and then in a second step, to elevate this new observation with respect to outlierness. And then in a third step, I make a distinction. If the current observation is no outlier, then I add this observation to the data and make a model update. If it is an outlier, I make no model update, but continue with a new prediction with the existing model one step ahead. So how does our approach work in practice? Unfortunately, due to the lack of labeled data, we can't give any hard performance numbers, but we are stuck to visual inspection of the results that for the 4 data stream examples you can see here. And also, of course, to the feedback of the customer that was very positive. So one can see here that all the red points are detected as outliers, and this is exactly the outcome that was from the visual inspection wanted by the experts at the industry partner. Maybe to summarize our proposed outlier detection approach, the advantages are that it works in highly heterogeneous and evolving data sets of different machines, as we saw at the examples shown. It's robust even in presence of a high amount of outliers. It's applicable to streaming data, and one can online calculate for each arriving data point if it's an outlier or not. And it's applicable in an unsupervised setting. And we thought this proposed approach might be interesting for many different industrial applications. Maybe what I don't want to hide is that, of course, arriving to these results, it was not just a one-shot learning, let's say, but it was a hard work of calibration. So we had repeated feedback loops and discussions with our industrial partner, and this was necessary due to the lack of historical labeled data. So if we would have labeled data, we could make the optimization of the controlling parameters automatically. But once when this calibration was done, our experience is that it really is very robust, and as I said, this detection algorithm runs simultaneously on several hundred machines and gives really good results. So thanks for listening to me.
Okay, thank you, Johannes, for your presentation. Very nice, very interesting.